This video is about adding and subtracting rational expressions. And to do this, which is in the context of algebra, intermediate algebra, or sometimes there's overlap before and after that course with this topic, we're going to recall some of the basics that we already know from arithmetic with fractions. So let's suppose I simply wanted to add 2/3 plus 4/7. Well, you may recall that in order to add or subtract fractions, you have to have what's called a common denominator. And so we'd have to find that here because we don't have one in common yet. They're 3 and 7. So the least common multiple of 3 and 7 would be 21, and that will serve as our least common denominator. So what we end up doing is writing out two brand new but blank fractions, but each with a denominator of 21, this newfound least common denominator. And then we have to go back and adjust things, possibly, so that that denominator is true of the entire fraction. So in the first fraction here, I had a 3, but now it's a 21. So the question is, what would I have to multiply that 3 by to get the 21? Well, 3 times 7 is 21. So whatever I multiply the denominator by, I would also have to multiply the numerator by. So I also multiply by 7 on top. So now my numerator is 2 times 7, which is 14. So it actually changed the numerator. We have to do the same thing with any fraction where the denominator changed. So in the second fraction, it was a 7. Of course, you'd multiply that by 3 to get the 21. But therefore, we also multiply the numerator by 3. 4 times 3 is 12. And so there's our new set of fractions. It's really 14 over 21 plus 12 over 21. Once the denominators match, then you simply add across the numerators. So 14 plus 21 is 14 plus 12 is 26. That's the numerator. We added it straight across the top. But then we just keep the common denominator as the denominator, 21. So we do not add across the denominators. Once they're the same, we just keep it. So 26 over 21. Okay, that's a review of the process for adding or subtracting fractions from arithmetic. Well, it turns out that when they have rational expressions, so fractional or algebraic terms with variables involved, the process really isn't much different. In fact, the larger process is the same. It's just some of the details of finding the common denominator and adjusting the fractions can look different. So let's begin with some notes that say this. To find a LCD with variable expressions, we're going to do the following two steps. So first, we're going to factor all denominators. Well, we've been factoring a lot lately, so that should be no surprise to us. Secondly, we're going to multiply together a couple things. The numeric LCD of those denominator factors. You may have just numeric or constant factors in the denominators, and those factors would have an LCD just in terms of arithmetic like we did here above in this example, this warm-up example. So you're going to multiply that numeric LCD with the highest power of all variable factors. So that would be comparing any variable factor and then picking the highest power of that certain base to represent all those similar base variable factors. So let's do some examples to see how this actually shows up and looks. Our first one is 7 over 2x squared plus 4 over x. Now, these do not have the same denominator, which means we'll have to find a common denominator, or LCD. And that process, as we just described above, involves factoring all the denominators. But you'll notice that these denominators are simple enough to where they really, I can't say they can't be factored, but there wouldn't really be much use to factoring them. Like you could turn the x squared into just x times x, but that's not much use. So we're going to just leave them as they are and expect that they're already factored. But we're also now going to go through step 2 of finding the LCD, which means we're going to multiply together the numeric LCD. Well, we do have a numeric factor in the first denominator, the 2, and we don't have a visible numeric factor in the second denominator, but you could really imagine a 1 coefficient in front of the x there. So in that way we do. And the common denominator for 2 and 1 would be 2. So that's going to be part of our overall LCD. But then we're also going to use, as it says here, the highest power of any variable or all variable factors. Well, the only variable factors we're seeing in these denominators would be the x squared and the x. Notice those are the same base. They both have just a simple x base, but they have different powers. And our instructions say we have to multiply the highest power that we see. So I'm going to use the x squared as the highest power. That higher power will represent even the lower one, just the simple x. So 2x squared is our LCD. Well, in keeping with our process that we did with the arithmetic above, we're going to rewrite both fractions just as blank first, but with the LCD in place. So 2x squared is the denominator of both fractions. Then we go back and compare them with the originals and say, well, did any of those denominators change? And if so, how? Well, the left fraction actually already had the 2x squared denominator, so we don't change the numerator at all. It all stays the same. But the second fraction was different. That denominator was just x. Now it's 2x squared. So the question becomes, well, what would I have to multiply the x by so that it would turn into this new 2x squared? And the answer is 2x. But then I would have to multiply that exact same thing above with the numerator, which was 4. But now if I multiply that by 2x, 4 times 2x would be 8x. And so there's our new set of fractions now with a common denominator. Like we did above, once you have a common denominator, you simply add or subtract across the top, the numerators. So that would be 7 plus 8x. Of course, those aren't like terms, so we'll just leave them as they are, 7 plus 8x. And that's all over 2x squared, and that's where we would stop. All right, let's try another example. The second one begins with the first fraction having 7x in the numerator, and that is over x squared plus 2x minus 8. Then we have a plus sign, and then a second fraction which has 3 in the numerator, and then x squared minus 3x plus 2 in the denominator. So clearly we have different denominators. We'll have to go ahead and get an LCD for them. But as we said above with our steps, you actually can't find the LCD until you factor the original denominators. So we're going to factor those first. And to do so, we'll just recall our factoring method. These are 3-term polynomials. You could do, guess and check, product sum, those things. That original, or that first original fraction with the x squared plus 2x minus 8 could be factored into 2 binomials, which would be an x plus 4 and an x minus 2. And then we're going to keep the numerator as is for now, just 7x, and move on to the second fraction. Again, we'll factor that denominator, which originally was x squared minus 3x plus 2. If we factor that using maybe a product sum method, we'd have an x minus 2 and an x minus 1. And of course, we'll keep that numerator the same as well, just 3. Okay, now after factoring the denominators, we are now ready to find our LCD, our least common denominator, and we'll use our instructions above, which say first look for any numeric factors. Well, there aren't any. There aren't any single number factors in either denominator, so we can just skip over that part. The second part says use the highest power of every unique factor in any denominator. So for this part, we're just going to go left to right and make sure we've captured that. The first factor in the denominators from left to right is the x plus 4. Well, there's no higher power of that factor anywhere else in any of the other denominators. So in other words, there is no x plus 4 squared or x plus 4 cubed or something. X plus 4 is the highest. It's the only one. So we use it. So x plus 4 is a factor in our common denominator, which means we can now check it off and then move on to the next one. So moving left to right, we have now x minus 2. Well, there is another x minus 2 in the other fraction. And notice, though, it's a singular x minus 2 as well. So x minus 2 to the first power is all we have. All we have to do is pick the highest of those, which would be, well, just x minus 2 to the first power. and that would represent all of the x minus 2 bases. So one in each of those fractions. Then we move on. The last factor is the x minus 1. Of course, there is no other x minus 1 anywhere else, so we use this one as its highest representative, highest power representative. And so our LCD is done. We've gone through all the factors in our denominators that are in factored form and found the highest power of any factor in them to represent them in the LCD. Once we find the LCD like we've been doing, we're simply going to rewrite both fractions, but now doing so with the LCD as the denominators. So x plus 4, x minus 2, and x minus 1 all being multiplied together, and that occurs in both fractions denominators. Okay, so once that's all written down, there's a lot of writing in this process, we go back and then make adjustments as necessary, as you may recall. So we go back to the first fraction and notice it's different. It changed from one step to the next. In fact, that first fraction was missing something. If you compare it with the new one, it was missing the x minus 1. So we have to put an x minus 1 as if it were being multiplied by that original denominator. But that will help us remember to put an x minus 1 multiplied in with the numerator as well. Now, with that being the case, we would multiply the 7x times the x minus 1 by distributing it in, which would give us a brand new numerator of 7x squared minus 7x. So we've now recreated the first fraction, but now with the common denominator we were expecting to use. So we'll go on to the second fraction and basically do the same, looking for what it might have been missing. And there you'll notice it was missing the x plus 4 factor that was not in the second denominator originally. So we'd have to multiply that by that x plus 4 to make up for it and get this new one, this new version of it. But that would mean we'd have to multiply the numerator also by x plus 4 and then distribute the 3 as expected here to get 3x plus 12 as the new numerator for this second fraction. But the good news is now that we have a common denominator in place, and so to do this arithmetic, we'll simply add across the top. We're adding these fractions, which really means combined like terms. So let's rewrite this all out again. This is really 7x squared minus 7x. Then really there's a plus 3x and then a plus 12. And we could write that all over the LCD that we've already found of x plus 4 times x minus 2 times x minus 1. And then, as mentioned, we'll just combine like terms in this numerator to get 7x squared, and then minus 4x, and then plus 12. And that's all over our LCD of x plus 4, x minus 2, and x minus 1 all being multiplied together. Now, we are likely done here, but sometimes at this step, even after doing all this work, you're not done. And the way you might know is maybe it's such that I could factor the numerator as I now have it in its combined like terms form, and in doing so, find a factor that would match one of our denominator factors, which would mean we have to cancel them to reduce the result. So you would always want to check that, and to do so, just use any of your factoring methods for the 3-term trinomial you see in the numerator there. But you will find that it's not going to match any of the factors, even if it were factorable, which it's not. You could double check that. It's not going to match, and therefore won't cancel, and therefore won't reduce, which means we can stop right there. Let's try our next example. This one begins with a fraction first as x squared minus 39 in the numerator. In the denominator, we have x squared plus 3x minus 10. Then we're subtracting after that another fraction which has a numerator of x minus 7 and a denominator of x minus 2. Now, we want to get a common denominator. Clearly we don't have one yet, which means we're going to want to rewrite this in factored form as we've been doing. Now, the second fraction is not really factorable. The x minus 2 is already prime. You can't go any further with that, so we'll just recopy that second fraction. But the first fraction has a trinomial denominator that is suspiciously possibly factorable. So you can go through your factoring methods on it. I'm just going to copy the numerator down, the x squared minus 39. With x squared plus 3x minus 10 in that denominator, you could factor that into an x plus 5 and then an x minus 2. Again, try your product sum methods, your guess and checks, anything you prefer on those, that works fine. There, we can then find the LCD. So actually, let me write out what that would be first before we proceed. So remember, we want the highest power of any unique factor in any denominator represented. So for that, we'd start left to right and say there's an x plus 5. I don't see any other x plus 5 anywhere else. So we use x plus 5 as its own highest representative. Move on to the x minus 2. You'll notice we do have another one in the other fraction, but it's also a single x minus 2. And so the highest power of those is just a singular x minus 2, which means there's the LCD, x plus 5, x minus 2. So as we've been seeing, we're going to rewrite this whole list of fractions here, where the denominator for each is now this common denominator of x plus 5 times x minus 2. And then we have to look back to see if any adjustments are necessary. So you'll notice that the first fraction already had this exact denominator, which means we'd make no changes to its numerator either. We just copy that down as x squared minus 39. But the second fraction had a different denominator. It was just an x minus 2, which means we'd have to multiply it by the x plus 5 to accommodate our LCD, but then also do that in the numerator, so that our new numerator is, well, it'd be an x minus 7 times an x plus 5, and you could just FOIL that out now, I suppose, or next, but I'm going to save rewriting everything a step and just FOIL that out now. That would be an x squared minus 2x minus 35. Now that's just doing the FOIL on this numerator binomials we have there. Now, at this point, we have the common denominators in place. We're ready to combine like terms in the numerator, but there's a really key step here that's easy to gloss over or forget. And when we have this negative sign in between the fractions, in fact, let me color coordinate that somehow here. So let's say we have a negative sign in between the fractions. A negative sign always applies to the numerator, but every term. So you'd have to distribute this negative sign to all the terms in the numerator following it, which would result in the following. Our entire numerator, if I put that all together, would end up as x squared minus 39. That's from the first fraction. Then we would have minus x squared plus 2x and then plus 35. That's after distributing the negative sign to all the like terms in that second numerator. And that's all over our LCD of x plus 5 times x minus 2. So now we'll combine like terms in the numerator. We notice we have an x squared minus an x squared. Those just cancel out, which leaves us with a 2x as that highest term power. And then minus 39 plus 35 would be just a minus 4, so 2x minus 4. Then down below, of course, we have the x plus 5 times x minus 2, LCD still in place. Okay, you may say, great, we're done, but remember, if you can factor and reduce further, you should. And it turns out in this case that we actually could. Look at the numerator. There's a simple GCF of 2, and if I factor that out, I'm left with an x minus 2 behind it. But that means if I copy down this LCD, there's an x minus 2 in the numerator and the denominator, and those would therefore match and cancel, which means our final result would simply be what's left in the numerator over what's left in the denominator. So 2 over x plus 5. All right, let's try one more example of adding and subtracting rational expressions here. This one begins, it has the first fraction has x minus 1 in the numerator, and then x squared plus 2x plus 1 in the denominator. Then we have the subtraction sign, and then the second fraction is 3 in the numerator, and 2x minus 2 in the denominator. Then we have a plus sign, and then we have a third and final fraction, which is x in the numerator and x squared minus 1 in the denominator. Now, as we've been seeing, we have to find a common denominator, because this certainly does not start with 1. But to do that, we have to factor all the denominators. So we're going to go ahead and rewrite these in factored form. And the first denominator being x squared plus 2x plus 1, that is what you could call a perfect square if you're used to that form, or if you use like a product sum or something, you've got an x plus 1 times an x plus 1. Now, if that were a perfect square and we factored it using that formula, we actually would have written that as x plus 1 squared, which I'm going to write in quotes here below this denominator because I really want to refer to that importantly in a second. So I'm going to write x plus 1 times x plus 1 as x plus 1 all squared, which is really what it is, but I purposely want to show that. Okay, let's keep going. In the next fraction, we could factor a GCF of 2 out, which would leave behind an x minus 1. Of course, we're not changing the numerators yet, so I'm going to leave those in here. The first one was x minus 1, the second one was just a 3. And then lastly, we have a difference of 2 squares, the x squared minus 1. For that last denominator, that would, as we know, factor into an x plus 1 times an x minus 1. And then we'll keep that original x in the numerator. Now, once everything is factored, we can go ahead and put together the LCD using our definition far above here that we wrote out to do that. And that means we want to go through every factor and pick out the highest power of it anywhere, including any numeric LCD. So notice we do have a numeric factor, the 2, which is a factor in that second denominator. So there's no other numeric factor, which means 2 will do it as our numeric LCD. I guess you could say there's a 1 in front of the others. But even if you do think of it that way, then the LCD of 2 and 1 is still 2. So there's our numeric least common denominator. Then we're going to go through left to right to find the highest power of any common variable factor. So the first fraction has the denominator, which remember originally we factored it as x plus 1 times x plus 1. Then I rewrote it as x plus 1 squared. The reason I did that is because, remember, we're looking for the highest power of all these factors. And if I have an x plus 1 squared, notice I have another x plus 1 way down in the third fraction, but I would only want to use the higher power of those, which is actually the x plus 1 squared. So I'm going to use x plus 1 squared in my LCD, and that will represent all the x plus 1s. So I like to write, even if it ends up being like an x plus 1 times an x plus 1 or something similar, I like to write that as x plus 1 squared in the problem because then it's visually a reminder, oh, that's right, that is the higher power. Otherwise, it could be possible to accidentally say, well, I only have one x plus 1 here, and 1 here, I guess 1's the highest. No, you actually have 2 in that first fraction. Okay, moving on, that takes care of that entire first denominator. The second denominator, we already counted for the 2, I should check the 2 off. Then there's an x minus 1. There's another one of those in that last fraction, but they're both singular, so a single x minus 1 is the highest power of that factor in the denominators. So we have an LCD. It is 2 times x plus 1 all squared times x minus 1, which means we'll proceed as we've been doing so far, which is I'm going to rewrite 3 brand new fractions, but I'm going to put the correct signs between them and this new LCD in each of their denominators. So they're each getting a 2 times an x plus 1 squared times an x minus 1 all the way down. And then we're going to go back and do the comparison that we've been doing to make sure and adjust the numerators as necessary. So the first denominator, if you compare the original with this new LCD, was missing something. It was missing, notice it had an x plus 1 squared, so we have that. It was missing a 2, because now we have this 2 factor, and it was missing an x minus 1. So we have to multiply that original numerator in that first fraction by 2 and x minus 1. Okay, going on to the second fraction, if you compare that with the common denominator, it was missing really just the x plus 1 squared. If you compare that, it was missing the x plus 1 squared compared to the new one, so we're going to have to put the x plus 1 squared in multiplied with that numerator to adjust it. And then thirdly, that original fraction was missing the 2, and it was missing the another x plus 1. I'm going to have to fit these in a little bit below. So we're missing the 2 and another x plus 1 because we have to have x plus 1 squared. We only had a single one there. So that was missing, but that's all of it. So now I have to multiply that numerator by that same thing. So 2 times x plus 1. So the extra x plus 1 will make up for the squared. We're good to go. Now we have to just write out what these summarized new numerators would be. If I clean that up by multiplying and combining like terms, the first numerator would end up being, really it's a 2 times, it's x minus 1 times x minus 1. If you put that together, that's really x squared minus 2x plus 1, if you just FOIL those together. And then moving on to the second fraction, that numerator had a 3. Now we're multiplying by x plus 1 squared. Well, similarly, that would be a 3 times x squared plus 2x plus 1. And then the third fraction as well, it only had an x, but now we're multiplying by 2 and x plus 1. So now we have a 2x times an x plus 1. If we distribute everything across all these numerators and then combine like terms, which is quite a bit to do, let's see, I'm going to write this all out here in line. In the first fraction, we'd end up with a 2x squared minus 4x plus 2. In the second fraction, be careful with this. There's a minus sign between the first and second fractions. Really, that minus sign should go with the 3. That is this numeric coefficient, and those together should be distributed in to the parentheses which follow. That would result in a negative 3x squared, and then a minus 6x, and then a minus 3. And then in the last fraction, we'll distribute the 2x in to get a positive 2x squared, and then a plus 2x. Okay, now that's the numerator. That's all over our LCD, which is, of course, 2 times x plus 1 squared times x minus 1. And at this point, we want to combine like terms in the numerator to simplify as much as we can. You'll notice we have some x squareds to combine. We have a 2x squared and a minus 3x squared. And then let's not forget this last x squared term here near the end is plus 2x squared. So combining all those together, we'd end up with a positive 1x squared, or just x squared. Then if you combine the x terms, we have a minus 4x, a minus 6x, and a plus 2x. Those are all like terms. If we combine those, we should end up with a negative 8x. And then with the constant terms, we have the plus 2 and the minus 3. Altogether, that's just a minus 1. And so we have x squared minus 8x minus 1 all over our common denominator of 2 times x plus 1 squared times x minus 1. And then, of course, you should check to make sure that this can't be reduced further, right? If the numerator was factorable in a way that would cancel with something in the denominator, we should do it. But you can do a quick product sum check on that, and you'll find it's not going to work. It's not factorable. So that's where we'll leave it.